Hello and welcome back to the CCENT journey with me, Ryan, and in this section we're going to start a new topic called DNS, Domain Name System. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So first of all, before we dive into DNS and the configuration of it and actually seeing it in action, we first need to understand why we need DNS, what it actually does for us and why the technology was invented. And then we need to make sure we know the facts about the technology. So I put together 4 points here that'd be worth going over. First of all, what does DNS stand for? It stands for Domain Name System. It's used by devices to resolve names to IP addresses. So what does that mean? Well, if you think about your PC today, let's primarily talk about web browsing. So you open up Chrome, Firefox, Internet Explorer, whatever it is you're using, and on that page you obviously have at the top your toolbar sections and, more importantly, your actual address space. And in the address space you type in your HTTP, www. whatever you want it to be, let's say google.com. Well, your PC needs to take that address or take that name, which is correctly referred to as a URL, a Uniform Resource Locator, and it needs to understand that if www.google is your destination, the PC needs to understand what is google.com, because we as humans remember names, we remember Google, we remember Yahoo, YouTube and all the other websites, but the PC doesn't know what Google is. All it knows is Google must be some IP address out on the internet. So there needs to be a database of human-friendly URLs or names and a corresponding IP address for the PC. So ultimately, a DNS server, which is normally out on the internet, which we'll talk about in a moment, is a list of URLs, a database of URLs, with its corresponding IP ranges. And your PC, when you type in your URL, needs to be able to communicate with a server where all this information is held to be able to find the equivalent IP addresses. Because when you type in google.com, your PC, like I said, needs to go find out what is its counterpart, what is the IP address to google.com. And that is what DNS at its fundamental level is trying to achieve. Now, DNS is a huge topic. There's all different types of records, there's different types of security. DNS can be used for all sorts, but as far as the CCENT is concerned, we need to know what really an A record is. We need to know what a DNS server is, and where in the DNS, where in the process of communication does DNS arise? Why do we need DNS? How can we troubleshoot DNS faults, and how is the basic configuration of DNS done on a Cisco router? Those are the things we need to be learning about. But before we can get started, we need to understand where it comes into play today. So it's used by devices to resolve to IP addresses. You type in a URL or a name into a browser. Your PC needs to translate that to an IP address. And the way it translates that is it queries a DNS server. And that DNS server has the bindings or mappings or records, would be the correct terminology, for the URL to IP address, and it's able to give your device google.com's IP address or yahoo.com's IP address in order to allow the lower layers to process that data correctly. So what else do we have to know about it? Server stores a bunch of different records. So like I said, records is the right terminology, because in DNS we have different kinds of records. We have A records, we have MX records, we have CNAME records, and ultimately what this is, like I said, an A record at its fundamental level is a mapping between an IP address and a name. That's all that an A record is, and they're all stored in a server out on the internet. These servers are provided by people like Google. They're provided primarily by people like your ISP, and you as a corporation or business will either have your own local DNS server, and there's benefits and downfalls of doing that. And then maybe your DNS server relays queries to someone else if you don't have it inside your database. Because the other thing you need to remember is there are obviously a ton of addresses out there, a lot of records that need resolving, and it's very rare that you'll come across a server that has every record. So we have things like DNS forwarding or different resolver groups before you reach what we call the root level of DNS. And that's where every record is stored. So server stores a bunch of different records. The main one that we really want to focus on is the A record. Now I doubt the terminology actually called an A record would appear on the CCENT certification. Same is true with the MX records. But it's important to understand that what they're trying to achieve and what they actually are. Because in the real world, if you have a website or if you have a mail server, then MX records and A records will become an important part of that to make sure that you have reachability to your website. Because if there is no DNS, there is no websites. Because nobody wants to remember the actual exact IP address to reach a destination, because we as humans are not very good at remembering boring numbers that don't relate to anything. And 2, if you don't have an actual name that resolves to an IP address, then people aren't going to find you in places like search engines. And lastly, as far as the CCENT is concerned, most, if not all of the communication you'll see is on UDP port 53. Now there are communication on TCP port 53, but for now, if it comes up as a question, we need to be remembering UDP port 53. So some of the things to remember there. What does it stand for? It stands for Domain Name System. What port does it use? It uses port 53 and it's UDP. What does UDP mean? It's unreliable, but it's fast. We don't want TCP because it will slow down the communication. Because remember, if you're on a PC and you type in google.com, you want the actual resolution of the DNS to be extremely quick, because until the resolution is completed, there is no traffic going to the actual final destination, because that resolution has to take place first before traffic can flow. We need to know that there are servers out on the internet that store the different records, and those records are the translations between IP to name, and ultimately this is the backbone of what DNS is doing as far as the CCENT is concerned. And I say as far as the CCENT is concerned because, like I said, DNS in its right is a very big topic. There's things like mail servers, CNAMEs and so forth, but for now all we need to know about is the basics of DNS. So let's look at 2 things here. First, let's refresh our minds on how communication kind of works and how DNS influences and changes that communication. So in front of us we have a small diagram that I've created, a couple of PCs, a switch and a router. Let's give the PC an IP address. Let's give the router an IP address. So this is going to be 192.168.0.254 because it's inside a /24 and we're not too bothered about the PC down the bottom. Let's say the router uplinks to an ISP or to the internet, and out on the internet there's a server that we wish to communicate with. Let's say it has the IP address of 1.1.1.1.1. However, we don't know it as 1.1.1.1. We know it as a URL, a uniform resource locator, or a name of a website. Let's say it's www.ryan.com. So that's the URL, and that ryan.com is hosted on this server, and this server has been assigned this public IP address. So what we've done is we created an A record, and that A record is stored on a DNS server, and that DNS server also lives out on the internet. So DNS server, and then let's say this is 8.8.8.8, which some of you may or may not recognize, but ultimately that is the IP address for Google's DNS server. So what we do is we go ahead and first of all ensure that our PC has a DNS server. So how can we check whether we have DNS servers on our PC? We can use the ipconfig, and ipconfig shows you the IP address, it shows you the default gateway, shows you the subnet mask, and you can add a switch or an extension or whatever you want to call it on the end of ipconfig called /all. So if you typed in on your Windows box ipconfig /all, it would give you even more information like the MAC address. I don't know, top of my head, I can't remember if ipconfig or ipconfig all shows you the DNS. Let's have a look quickly. So here is my command prompt on my actual PC. If I type in ipconfig, if is a Linux command, and you can see I have the link local address, which is the IPv6, which we'll get into later, and we've got my IPv4 address and so forth. If we then put the OR on the end of it, you can start to see that I have different interfaces. But most importantly, if we scroll up to the interface that we're interested in, which is the one I'm using to break out to the internet, you can see we have the actual IP address of my PC, and this is my actual PC. Time, date, my default gateway, the DHCP server, which is quite interesting. Don't see that very often on these outputs, but this is what we're interested in. DNS servers. You can see I have two, 8.8.8.8 and 8.8.4.4. So my PC will query these DNS servers for the A records that I require in order to resolve the URL to IP translation to give at layer 3 the correct destination when building that packet. And that's what we're going to explore now. So to find out the DNS on a PC, it's ipconfig, and then we have to use the /all in order to do it from the command prompt. Or if you go onto obviously your control panel, you can look at your NIC settings, your network interface card, and have a look at it through the GUI rather than having to use the command prompt. But it's always a good idea to know which command on a Windows box, a Linux box, a Cisco pulls up the DNS servers that are being used for that device. Normally they're given to you by your DHCP server. If you remember in the previous videos, we said that DHCP has a bunch of options to determine what it hands out, but one of those options is the DNS service, and that's who gave me my DNS servers. Okay, so let's get back. So let's go over the step-by-step of how this PC down here will communicate with Brian.com. Now, first of all, what's going to happen is we bring up a browser and we type in www.brian.com, and that's going to initiate the HTTP GET message, and that GET message is going to be what we refer to as our layer 7, our layer 6, and our layer 5. So remember, layer 7 is where the HTTP sits. Layer 6 is going to be the presentation of that. So it's a HTML page, for example. And 5 is going to be where the session sits. The session is going to pass it on down to TCP because HTTP uses the TCP protocol, and it uses the well-known port of 80 as the destination. But now it's got a problem because at layer 3 it needs to populate the destination IP, but the PC doesn't know of the destination IP address because the only thing the user has put in is the URL. So now that communication string can't go any further. So a good way to think of it is it puts it on hold because I can't move any further but to the destination because I simply don't know the destination. So because of that, it needs to now send out a DNS request. And this is why we need to be quick with DNS, and part of the reason is why we use UDP. Because now a application needs a prompt for a DNS request. It's going to go down to UDP, port 53. The destination, in this case, is going to be 8.8.8.8, which is our DNS server. It's going to obviously put the Ethernet header on it, and that's going to be the source MAC of the PC, the destination MAC of the default gateway. So we've got the dest and the source, and of course the source IP will initially be the PC, which is the private address, and then when it reaches the default gateway, because we're going out on the internet, just like we learned, we need NAT, and part of NAT is most likely using PAT. So the source IP will then become the public IP on this interface, with the destination remaining 8.8.8.8. It will hit the DNS server. It will say to the DNS server, hey DNS server, as you can see I've got a UDP at port 53, so pass it to your DNS process, and I'm looking for a DNS request. Can you tell me the IP address for Ryan.com? It says certainly. The IP address, or the A record for Ryan.com, is 1.1.1.1, and it sends back a DNS response with the destination of this interface. It comes back in, it then gets translated, passed to the final destination. The final destination does the decapsulation, looks at the DNS response, and is able to populate a local cache to say, I know that Ryan.com is now 1.1.1.1. Going back to the original header, it's now able to populate the destination, and is able to populate the source, and is able to do the Ethernet header with the destination of the default gateway, the source of itself, and then obviously layer 1 out onto the wire, and is able to reach the final destination, which is out on the internet. So this whole process here happens as someone types it into the URL, or types URL into a browser. This is why it needs to be quick, because the communication which we require, which is to go and get a web page, can't happen until the DNS resolution happens. And this is why it's important to understand DNS and what it's actually doing, because if the DNS resolution doesn't resolve, is unable to communicate with the DNS server, it doesn't know about a DNS server, or the local cache is incorrect, then the actual final result is the initial communication requirement, which is to communicate with Ryan.com, will fail, and we need to be able to identify it's failing because of DNS. Now, one thing to keep in mind for this example is I said that the HTTP GET and the TCP header are built and then it pauses on the IP. Well, that's probably not true. I don't know necessarily how the application itself behaves. I would assume the HTTP element or the application will look at the local cache prior to building everything else, and then does the initiates the resolution through DNS, or maybe it does do the HTTP GET TCP and then prompts DNS. But either way, we don't really care about the order of operations. What we do care about is where does DNS sit, why is it so important to the communication, and how it can cause us to have certain faults in the network, like being unable to resolve, or being able to resolve but incorrectly or slowly. Okay, so that's all we've got time for in this lesson. Just to finish up with a quick review. What is DNS? We said DNS is the domain name system. It runs UDP at layer 4 and uses the well-known port of 53 for most of its communication. We know, looking at the example, the importance of using UDP was primarily related around the speed, because just like we've seen, if you're trying to access a website, that can't happen until the DNS has resolved and we got the actual IP address, because normally the end user will put in the URL, the actual name of the website, not the IP address, and we need to know the IP address in order to reach it. So because of that, we need DNS to happen quickly, which is why we use UDP. And we know it takes the URLs and finds out the IP address. The IP address to URL mappings or records are stored in DNS servers. A DNS server can be local to you at your premises if you're a large corporation, or they're remote, given to you by an ISP or a third party like Google. We went through how it actually works. We've seen the communication of how someone would communicate with a web server. If you don't know the IP address of it, you only know the URL. We've seen how it then has to invoke DNS to perform that resolution in order to continue with the initial communication. So there's a lot going on there. Like I said, there are some facts you need to remember about DNS, but most importantly, the reason we need to know about DNS is so we can actually troubleshoot it in an everyday environment, because it's not always clear that DNS is causing the issue. And as long as we know where it sits in the network and how it behaves, we can then troubleshoot it accordingly. I hope this video has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.